Okay, so the paper we're jumping into today is called Agent-R1, Training Powerful LLM Agents with End-to-End Reinforcement Learning.
Right. And it really tries to solve what is probably the biggest headache in agent development right now.
Which is making reinforcement learning actually work reliably for these tool-using models.
Exactly. The core idea, if you boil it all down, is that they took the classic framework for RL, the Markov Decision Process, and they systematically redefined it for this new world of LLM agents.
So they redefined the basics like state, action, and reward to fit an agent that's constantly interacting with outside tools over many, many turns.
And to make that theory practical, they built Agent-R1. It's a training platform, a really modular one, that's built from the ground up for this kind of end-to-end multi-turn training.
And the secret sauce seems to be this combination of dense process reward, so rewarding the small steps along the way, and then this very clever action masking.
That combination is key. It lets you assign credit really precisely. You know exactly which action led to a good or bad outcome, even in a super long conversation.
And the results seem to speak for themselves. In their tests on multi-hop question answering, the agents trained this way just blew past the baselines, like standard RAG. It shows this method really works.
Okay, let's unpack that a bit, because it feels like we've been hearing forever that LLMs are moving beyond just writing text.
Right, from static tasks like code completion to becoming these full-on agents that have to reason and make decisions in the world.
And what's so fascinating is why that's such a hard transition. A normal LLM task is, well, it's static, single turn.
You give it a prompt, it spits out an answer,
Yeah,
end of story.
Exactly. But an agent needs to make a sequence of decisions. It has to keep a memory, a context, over dozens of turns potentially, and it has to react to feedback from the environment that can be stochastic.
Meaning things can go wrong. An API can fail or return something unexpected.
Precisely. And that's why you can't just take a standard LLM and throw RO at it and expect it to work. We've seen it succeed in really narrow domains like math, but for these general autonomous agents,
it just falls apart. You get instability, it doesn't generalize, and it's almost impossible to figure out what a good reward signal even looks like.
that's the core of it. If an agent takes 10 steps to get an answer, and you only give it a tiny reward at the very end, how do you tell it that step 3 was brilliant, but step 7 was a mistake?
You can't. You need a better foundation. And that's what the Agent-R1 authors realized. They had to go back to the drawing board on the Markov decision process itself.
This is their biggest conceptual leap, I think. It's about really defining the difference between a static LLM and an LLM agent. Let's start with the state.
Okay.
For a simple static model, the state is just the prompt plus whatever tokens it's generated so far.
Yeah.
Its whole world is about predicting the next word.
But for the agent, that's not nearly enough information.
Not even close. For the agent, the state has to be the entire interaction history, every turn.
So the agent's action and then the environment's response to that action.
Every single time. Think of it like a case file. It needs the complete record to make a smart decision about what to do next. It's not just a scratch pad.
That makes sense. So what about the action space? That must change too.
It does. I mean, fundamentally, the model is still just generating text. But now, certain sequences of tokens aren't just words anymore.
They're commands.
Exactly. They are interpreted by the system as a command to call an external tool. So the text output becomes a real-world action, an intervention.
And that intervention is what makes the whole thing stochastic, right? With a normal LLM, adding a token is deterministic. You know exactly what the next state will be.
Right, that's what they call a generative transition. But when an agent uses a tool, that triggers an environmental transition.
And you have no idea what that tool will return. The search API could find nothing, or the code interpreter could throw an error.
Precisely. The next state of the world is now uncertain. And that brings us to the reward.
Which for normal text generation is usually just a sparse reward at the very end. Did it get the right answer? Yes or no?
A model can't learn from that in a 10-step process. So for the agent, they use a dense, granular reward structure. You still get a final reward for the outcome, sure.
But you also get these little rewards along the way.
Yes, these crucial intermediate process rewards. Things like, did you format the tool call correctly? Great, have a small reward. Did you pull a key piece of information from a search result? Perfect. Another small reward. It guides the agent.
Okay, so you have this really elegant theoretical model, the extended MDP. But how do you actually build a system that can manage all of that complexity in practice?
That's the engineering side of the paper. And that's Agent-R1. It's a platform they built specifically to handle these messy multi-turn rollouts. And they did it by creating a very clear separation of concerns.
Yeah.
They split the work into two main components, a tool module and a ToolEnv module. It's a division between execution and interpretation.
Okay, let's start with the tool. That sounds like the simpler one.
It is. The tool module is just the executor. It's the calculator or the search API connector. Its only job is to run its execute method and return the raw factual result. It just reports, this is what happened.
And they have some standardization in there, right, with JSON schemas?
Yes, and that's a really smart engineering choice. It forces the LLM to learn how to generate perfectly formatted API calls, which gets rid of a whole class of silly errors before you even start the hard part of RL training.
So the tool is the executor. Then the ToolEnv must be the orchestrator, the brains of the operation.
Exactly. The ToolEnv manages the whole RL environment. It takes the agent's text, figures out if it's a tool call, tells the tool module what to do, gets the raw result back, and then it interprets that result.
And this is where the reward comes from.
This is it. The ToolEnv step method is where the magic happens. It decides, based on that tool output, what does this mean for our goal? And it calculates and assigns the appropriate process reward. It's what makes the whole system so modular.
So now you have these incredibly rich logs of everything that happened. The prompts, the agent's text, the tool outputs, all these little process rewards. But a lot of that text wasn't written by the agent. How do you apply the RL update to only the parts that matter?
That is the absolute crux of the problem, credit assignment. In this long, messy dialogue, which specific tokens should the agent get credit or blame for?
You can't just reward the whole thing.
You can't. And their solution is this really precise mechanism they call an action mask.
A mask, okay.
Yeah, you can think of it like a spotlight. It shines only on the tokens that were actually generated by the LLM agent. It filters out everything else, the initial prompt, the text coming back from the tool, all of it.
So it isolates the agent's actual learnable actions.
Precisely.
Yeah.
And once you have those actions isolated, you can calculate the advantage. And their advantage calculation is special because it's not just based on the final reward. It's explicitly built from all those dense process rewards you gathered along the way.
And this is where the alignment comes in. The advantage is aligned with that action mask.
Meticulously aligned. So if the agent makes a great tool call and gets a process reward, that positive advantage is applied only to the tokens that made up that tool call command, not the text that came before or after. It's incredibly precise.
And then in the optimization step, when you're calculating the actor loss, that mask is used again.
Yes. The loss is computed only over the agent-generated tokens. So you're only adjusting the probabilities for the things the agent actually had control over.
And meanwhile, the critic model is getting better too because it's being trained on all this rich data with dense rewards, so it can provide a more stable baseline for the actor.
And that stability is what allows the whole end-to-end process to actually work without collapsing.
So to prove all of this, they tested it on multi-op question answering, a really hard task.
A perfect test bed. You can't solve it in one step. It forces the agent to reason, find a piece of information, use that to find another piece, and so on.
And they used a pretty small model, right? Qwen 2.53b, and just one tool, a wiki search. So they were really testing the learning method, not just throwing a giant model at the problem.
Very much so. And their reward was tough. You only got the big final reward for an exact match on the answer, and you got penalized heavily for any syntax errors in your tool calls.
So you had to be right, and you had to be clean in how you got there.
You had to show your work correctly. And the results were, well, they were stark.
How stark?
The baseline, which was just a naive RAG system, was really bad. It got an exact match score of about 0.13.
Okay, so it was right about 13% of the time?
Yeah, pretty much failing.
Okay.
But get this, the weakest RL agent they tested, Reinforce plus 1, still surpassed that baseline by a factor of about 2.5.
Wow, so that's not a small improvement. That's a huge leap from 13% to, what, over 30%?
Exactly.
Yep.
And the best performing agents, like PPO and GRPO, were pushing towards 40%.
Wow.
That's a massive difference, moving from a system that's basically a toy to one that could be genuinely useful.
But the really convincing part for any engineer listening has to be the ablation study, proving that all these extra components, like the masks, were actually necessary.
Oh, absolutely. This is the crucial evidence. They tried running PPO without the advantage mask, the part that aligns credit precisely with the agent's actions.
And what happened?
Performance dropped significantly. The EM score fell from 0.37 all the way down to 0.31. You lose almost 20% of your capability just by making your credit assignment a little bit fuzzy.
And disabling the other mask, the loss mask, had a similar effect.
A consistently negative effect across the board. It just reinforces their whole thesis. In these complex, sequential, interactive settings, you cannot be lazy with credit assignment. Precision is everything.
So this really clarifies that making the jump from static models to real agents isn't just about more data or bigger models. It requires a new theoretical foundation, which they provide with the extended MDP.
And a robust engineering framework, which is Agent-R1, that can actually implement that theory. The results are clear. When you do RL the right way, with dense rewards and this precise masking, you get agents that are just flat out better at using tools to solve complex problems.
It really feels like a scalable foundation for training agents that can do more than just fetch a document. This is about teaching them to actually reason and act sequentially.
Which is where all the interesting applications are going to be.
So let's leave our listeners with a final thought. This work was a huge success, but it was validated using a single, fairly predictable wiki search tool.
Right.
So what happens next? Given the modularity of their framework, what new kinds of instability do you think will pop up when you ask an agent to use multiple different tools at once? Say, a Python interpreter, a database query, and a web search, especially when those tools might give you conflicting answers or have very different costs.
That's the frontier, isn't it? It's not just about using tools anymore. It's about tool selection, conflict resolution, and resource management. That's a whole new, even more complex RL problem that this work really opens the door to solving.